Yes, anything.
I started looking at number
Yes.
19 on page 234, and I'm not sure if it's
234, 19 on 234. Okay. We only did problem 9 here, so let's look at 19. The quantity of charge Q in Columbus that has passed through a point in a wire at the time is given by Q of t, which is t cubed minus 2t squared plus 6t plus 2. Okay. Find the current when t is 0.5. So the quantity of charge, so Q, quantity of charge, through a point in the wire up to time, okay. And what we have, t is in seconds. So in part A, we have t equals 0.5 seconds. And then in part B, for t equals 1 second. See example 3. The unit of current is in ampere, okay? At what time is the current lowest? So let's go back to example 3. Example 3 is on page 227. So I is dq over dt. So I is given by dq over dt. Don't get scared, this is a different class. You do what you want to do. Okay? So it says a current exists wherever, I'm just reading quickly through that example. Figure shows, 6 shows part of the wire, and so on. You fit the charge, the average current. If we take the limit of this area, we get I, so dq over dt. Thus, the current is the rate at which the charge flows through a surface. It is measured in units of charge per unit time. Good. So we're asked to find the current when t equals 0.5 and then t is 1. So any suggestions? So I'm asked to find I at 0.5 and I at 1. Right, right. So I find I as being q prime of t, which will be 3t squared minus 4t plus 6. And then what should I do next? Plug it in. Is that okay, Tony?
Yeah.
Do we need more?
No, I think I did something really stupid.
No, that's okay. That's okay.
No, this is fine. Thank you.
That's okay. We didn't get the chance to do this yesterday. Okay. What I would like to do now is a problem from page 233. Like, for example, 1 or 2, and you do 1. Which one would you like me to pick? Okay, 1 it is. So 1 on page 233. So we are given a function f of t, which is t cubed minus 12t squared plus 36t. And this is a long problem, a long set of questions we have here. Okay. Let's see first of all what this is. I only copied the function, but I didn't mention anything about it. A particle moves according to a law of motion. So this is a motion function or distance function. Okay. T is greater than or equal to 0, where t is measured in seconds, and this in feet. It's also s. I prefer f of t, distance function in feet, and t in seconds. That's y is greater than or equal to 0. Very good. First question is asking us to find the velocity at time t. What do I have to do in order to find the velocity at time t? Get the derivative. So then v of t is nothing else but f prime of t, which is 3t squared minus 24t plus 36. Do we agree with this function as being the velocity? Perfect. Part B. what is the velocity after 3 seconds? Yes, part B, v of 3. So 3 times 9 minus 24 times 3m plus 36. When you have this number, give it to me, please. How much? -9. Measurement unit? Excellent. Does it mean that this is a negative speed? No, it only shows the direction. If we consider this direction positive, it only means that the particle is coming back. So if the speed is positive, the particle is moving in the positive direction. And if the velocity is negative, it's coming back. Okay, this was part B. Part C. When is the particle at rest? Yes, but what do I set equal to 0? Absolutely, very good, excellent. Indeed, v of t is 0. When the velocity is 0, the particle is at rest. Okay, where is my velocity function? Right here. 3t squared minus 24t plus 36 is 0. What are the key words in this class? In any other class? Factor simplify. What works here? Yes, you're right. However, because it's an equation, I will simplify. But you're right. You're on the right track. So what will I simplify by? Not by a variable, ever. But by... Very good. Excellent. Let's divide both sides by 3. So t squared minus 8t plus 12. What did that come from? Equals 0. Good. So now I'm asked to solve this. I have to solve this equation, and I'm hoping that I can factor it quickly. And can I factor it? Yes. T minus 6, t minus 2. So it appears that the equation has 2 solutions, time in seconds, and they are 2 and 6. So one more time, this was part C. When is the particle at rest? Are we okay so far? Okay, perfect. D, when is the particle moving in the positive direction? Okay, so I have to look at the velocity function. Every time the velocity function is positive, the particle is moving in the positive direction. Every time the velocity is negative, the particle is moving in the negative direction. It's coming back. Okay, so this is part D. Let me write it. When is the particle moving in the positive direction? When is the particle moving in the positive direction? So the velocity function, one more time, is 3. Here I divided both sides by 3 because it was an equation. So 3t minus 6, t minus 2. This is the velocity function, correct? It was right here, 3t squared minus 24t plus 36. So 3 comes out, so t minus 6, t minus 2. I'm going to study the sign of v of t. Here's how I do it. There is no point in putting 3 in the study of the sign because 3 is always positive. But I have to put t minus 6. I have to put t minus 2. Then I have to put in the product, which represents the function, or just better, right, v of t. What is the domain? Where does t start? Say it again. T is time in seconds. It has to start at 0 and go to positive infinity. Okay, so t, 0, infinity. Good. In the chart, in the values of t, I have to put the value that makes this 0, and the value that makes this 0. Nothing else. I don't care for anything else. So what do I put in here? Yes, but in order, from left to right. So 2 and 6. In 2, in this row, under 2, what do I write? 0. In this row, under 6, what do I write? Good. Now, what is the velocity when t is 0? I'm sorry, when t is 2? Of course. What is the velocity when t is 6? Of course. We just determined them right here. Of course, we know that. Good. What is the sign of this t minus 6? It's a straight line, right? T minus 6 is a linear function. Does it have a positive slope? Does it look like this? Or does it have a negative slope and looks like this? Good. It means that comes from which values? Negative and goes to positive. Okay, that's all I need. Just plug in a number if you have any questions about that. The same thing with t minus 2? Very good. Good. So now v of t is the product of these two. So now I'm multiplying on the first subinterval, I'm multiplying two negative numbers. What sign do I get? Perfect. In the middle interval, I multiply a negative by a positive. What sign do I get? And finally, on the last subinterval, I multiply two positive numbers. Good. So here's my conclusion. Between 0 and 2, does the particle go in the positive direction or a negative direction? Right. Between 0 and 2, particle goes in the positive direction since v of t is positive. Is there another situation in which the particle moves in the positive direction? 6 to infinity. It moves in the positive direction, right? So I'm going to write union 6 to infinity. So I don't have to write it again. So between 0 and 2, union 6 to infinity, the particle moves in a positive direction. When is the particle coming back, in other words? I should not include 0 and 2 because it's 0 at that point. So allow me to just write this. 0 is okay maybe, but parentheses are better. Okay, so between 2 and 6, the particle goes in the negative direction since v of t is less than 0. Is this clear? Any questions? Okay, where am I now? E. Find the total distance traveled during the first 8 seconds. Find the total distance traveled. So E. Find the total distance traveled between 0 and 8. Okay. This is directly related to the previous question. So follow me for a second. So at time 0, for 2 seconds, the particle goes in the positive direction for 2 seconds. Then, for the next 4 seconds, the particle goes in the negative direction for 4 seconds. And then, from that moment on, infinitely, but since I have 0 to 8, for the next 2 seconds, it's coming back, right? So it starts at 0, goes this way 2 seconds, comes back 4 seconds, and then comes back 2 seconds. So I have 3 distances to worry about. The distance between 0 and 2, the distance between 2 and 6, and the distance between time 6 and time 8. One more time. The distance between time t equals 0 and t equals 2, the distance between time t equals 2 and t equals 6, and the distance between time t equals 6 and t equals 8. Since the direction is different, I have to use absolute value in all 3 cases. 2 of them will be positive. but I have to use the absolute value because I'm adding the distances. I'm adding the distance between times 0 and 2 to distance between times 2 and 6 to distance between 6 and 8. So that's the reason why the total distance must be the absolute value of s of 2 minus s of 0 plus the absolute value of s of 6 minus s of 2 plus the absolute value of s of 8 minus s of 6. Go back 3 pages before. Here is my distance function. In this distance function, I have to plug in 2, 0, 6, and 8. And I'm going to do it with a graphing calculator. So I go to the graphing calculator. Where is it? I thought I got it started. I guess I didn't. Sorry. Okay, I plug in y equals my f of t, which is x cubed minus 12x squared, and then plus 36t, 36x, and I go to second table. Of course, yes, I know. Stop. Okay, second and table said yes. Yeah, for some reason, as I said, it goes back to the default. Okay, second and table. And I want 0, I want 2, I want 6, and I want 8. So I have all these numbers. Are they that large? Let me look at my function. Yeah, that's why. See, that's what I wanted to say. It doesn't make any sense. Doesn't make any sense. Okay, I'm checking now. 12. That's why I don't. Oh. Okay, good. Very good. Thank you. So, okay. So here they are. I'll copy them in the absolute value. So I have 32 minus 0 plus 0 minus 32 and plus s of 8, 32 minus 0. As I mentioned, 2 of them, as we expected, 2 of them will not need the absolute value, but the middle one does. So 32 plus 32 plus 32, 96. What? Excellent. We'll draw the diagram in a second, which I already did. We can draw the diagram F. So here's a diagram. At time equals 0, it goes for 2 seconds in the positive direction. So this is t equals 2. Then from this point, it goes back 4 seconds. So this is t equals 6. Yes, I can do this so you see the direction. And then it goes this way too. T equals 8. That's the diagram that I showed you. Find the acceleration at time t and after 3 seconds. We're asked in the next G to find the acceleration. A of t equals f double prime of t or v prime of t. The acceleration is the rate of change of velocity. So I have the velocity, so the acceleration will be 6 minus 24. So 6t minus 24. They're also asking us to find the acceleration after 3 seconds, is it? Yes. So that will be 18 minus 24, and the answer is -6 measurement unit. Yes? Excellent. Indeed. Feet per second squared is the acceleration. When is the particle, graph the position, velocity, and acceleration functions. We'll do that with the graphing calculator. There's a calculator sign next to it. When is the particle speeding up, and when it is slowing down? So I'm more interested in this part. So age graph, all three, f of t, v of t, and a of t. And we'll do that in a minute. But more importantly, the question is now, when is the particle speeding up or slowing down? So let me make sure that we understand there are two different things here. When the particle goes left and right in the positive direction or negative direction is one thing. We're interested now in something else. We're interested to find out when is the particle increasing its speed and when is the particle decreasing its speed. In other words, speeding up or slowing down. So here's what happens. If two forces go together, meaning the velocity and the acceleration, if they work together, either in the positive direction or in the negative direction. In other words, if I put my foot on the gas, I give it acceleration. I increase the speed, right? So if they're going in the same direction, if the velocity and acceleration work together, the particle is speeding up, no matter what direction. So if they are both positive or both negative, the particle will speed up. However, if they are working against each other, if the velocity is positive but the acceleration is negative, or vice versa, the particle will slow down. Okay? So let's look at the following chart. I'm copying from the previous part. So I'm copying this, but not the whole thing. So I have t, 0, 2, 6, 8. I have v of t, and I have a of t, and I will make a decision. Here I'm going to say decide if it's slowing down or speeding up. I only studied the sign for v. So I have between, so this is 0 and this is 0. It's positive, negative, positive. Positive, negative, positive. Okay. Now I have to look at the acceleration. The acceleration is a linear function. Where is the acceleration 0? When t equals, where is the acceleration 0? Set it equal to 0 and tell me what time the acceleration is 0.
4.
Exactly, right? 6 times 4, 24 minus 24 will be 0, right? 4. I have to put 4 in the chart. Here is 4, right here. Okay, so again, is this a linear function? What is the sign? Or you plug in numbers. I just prefer thinking in terms of the linear function. So it's negative and then positive, correct? Okay, so I have negative and then positive. So what happens between 0 and 2? The two forces are working against each other. The velocity is positive, but the acceleration is pulling it backwards. So what does the particle do when the velocity is positive and the acceleration is against it? Slowing down. What happens between 2 and 4? The velocity is negative, the acceleration is negative, they are going in the same direction, they are going negative direction, but they are helping each other. So what does the particle do between 2 and 4? Yes, between 2 and 4, speeding up. Then I'm here between 4 and 6. The velocity is negative, but the acceleration is positive. The velocity goes this way, the acceleration goes this way. What does the particle do? Slowing down. So between 4 and 6, slowing down. Good. What happens between 6 and 8? The velocity goes this way, the acceleration, both vectors are going this way. So they're helping each other. So what happens to the particle between 6 and 8? Speeding up. Now, we're going to graph all three in a second. I just want to show you there is a problem somewhere in the book. I wanted to show it to you because I like the graph. They are not showing you the study of the sign, which I really don't like. It's kind of hard to read. If you have it in a chart, it's much easier to understand what's happening. Here, the particle is pulled in the same direction. It is moving, the figure 3, blah, 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 between 1 and 2, and when t, it's hard to read this. I think it's much easier to see the chart where the velocity changes signs or is positive or negative, and the acceleration is positive or negative. And it's easier to see what happens in these 1, 2, 3, 4 subintervals. But I do like their, which we're going to do in a second, I do like their graph. So we're going to graph all three functions right now with the graphing calculator. So, and we'll discuss this also. But let's see. The acceleration, as you see, is negative here, and it's positive here. The velocity is positive here, and it's negative here, and it's positive here. Forget about the distance. I don't care for the distance right now. Forget about, don't even look at the red graph. So between these two, you see the velocity is positive and the acceleration is negative. The particle is slowing down. In the next one, see, the acceleration is under, the velocity is under. Look what happens. Speeding up. In the next subinterval, the acceleration is above, positive, but the velocity is negative. The particle slows down. And last one, the velocity is positive, the acceleration is positive, the particle is speeding up. So final thing, let's go to the graphing calculator. Let me see, am I exceeding the time yet? No, okay. So in y equals, oh, please wake up. Okay, this was our function, right? What was the velocity? I can calculate it again. So 3x squared minus 24x plus 36. And then the acceleration is 6x minus 24. Okay, so I want to change the viewing window, of course. I'm not interested in what happens to the left-hand side of 0, so I want 0. I don't care what happens beyond 8, because the whole study is between 0 and 8. And negative 10, 10 may be okay, but I already see it here. I'm peeking in this little window. So I'm going to say negative 30 to 30 with a scale of 5. Not even that is good enough. Okay. So that's the function, a cubic function. I don't care for it. It will not tell me anything right now. But I do care about the red function, which is the velocity. And I do care about the third function, which is the acceleration. So as we discussed, when the acceleration is positive and the velocity is negative, as we have, it's slowing down. Between 2 and 4, both functions are underneath, so it's speeding up. Between 4 and 6, here it is, between 4 and 6, the acceleration is positive, the velocity is negative, so it's slowing down. And between 6 and 8, both of them are above the x-axis, the acceleration and velocity. That's why the particle is speeding up. Any questions? Any questions? Okay. I'd like to look at one more problem here from economics, and then we can move on. And thank you, Tony, for asking that question. So that really helped me. So let's look at 32. You'll have to do 31. Let's do 32. And that's on page 236. And here it is. The cost function for production of a commodity is C of X equals 339 plus 25X minus 0.09 X squared and plus 0.00, I see 3 zeros, correct me if I'm wrong, X to the third. Find and interpret C prime of 100. How do I determine C prime of 100? What do I have to find first? Exactly, C prime of X. Okay, can anyone give us C prime of X? Say it again. So you want to start it, you started in descending order. That's fine. That's fine. 0.0012 X squared, I agree, minus 0.18X plus 25. Do we agree with this? Good. So then C prime of 100 is, let's plug it in. When you have the number, please give it to me. 100 squared minus 18 plus 25. I can do this by hand. 0.0012, and this is 10000, and this is plus 7. So 4 zeros. So that's 12 plus 7 is 19. Measurement unit. So let's read this again. The cost function for production of a commodity is find and interpret C prime of 100. Say it again. Dollars per? It's a commodity, so whatever item. Yeah, good. Now the interpretation. C prime of 100 is called the marginal cost. And it equals the rate at which the cost is increasing at the production level of what? At the production level of 100. And you will see in a minute this cost is approximately equal to the cost of producing the 101st item. It predicts, if you want, the cost of producing the next item, the 101st. You can also write this cost of 19 per item. This cost predicts the cost of manufacturing let me erase the whole thing. The 101st item. Here's the next question. Compare C prime of 100, which is just this, with the cost of producing the 101st item. So that's part B. So let me read this back to you. This is the marginal cost. C prime of 100 is the rate at which, since it's positive, I have to say the cost is increasing. If it were negative, I would have said the cost is decreasing at the production level of 100. This cost is approximately equal to the cost of producing the next item, which is 101st in this case. This cost predicts the cost of manufacturing the 101st item. It predicts. So now the question in part B, let me erase this. So the question in part B is asking us to find the cost, the exact cost of manufacturing the 101st item. So part B, find the exact cost incurred if we want to produce the 101st item. How do I find the cost, the exact cost of producing the 101st item? Let's say I go to the market and I buy some product that is sold per unit. Let's say I buy 5 kiwis. And one day, and the next day I go back and I buy 6 kiwis. How do I find the cost, assuming nothing changes, and the quantity, the price per unit is not affected by the number of units I buy? Because they may say, okay, if you buy 10, we'll give you one for free. So no bargain, no bonus, no nothing, right? So today I buy 5, and tomorrow I go and buy 6, and nothing changed, the same price per unit. How will I find how much I paid for the 6th one? I know I paid $5 for the first 5, and I paid $6 for 6. How do I know how much I paid for the 6th one? Tony?
Today's cost minus yesterday's cost.
Good. So then how do I find the exact cost of producing the 101st or buying the 6th item in my silly example? No C prime. There was no rate of change here. C of say it again.
101 minus 101.
Of course. Of course. The cost that what I paid for 6 minus what I paid for 5 will give me the cost of paying for the 6th one. Correct? Perfect. So I go back to my cost function. I don't have it here. Okay. I have to put it in. Let's put it in. It's easier than plugging in twice. Although you can subtract, but let's do that. Okay. So what was it? Where is my cost function? Oh, I have it in the book right here under my nose. So 339 plus 25x. Keep an eye on what I'm doing here. Minus.
You can't see it.
Oh. You can keep an eye on me then. Okay, plus, sorry about that, 0.0004 x to the 3rd. Okay, so I plug in 101 and I plug in 100. What should the difference be? Exactly, of course, we know that. Okay, so let's see. So to manufacture 101, I have 2358. And to manufacture 100, I have 2339. And what is the difference? 19. Okay, so this is the price per the 101st item.
So essentially,
Yes.
in this, we would take the derivative of the cost, and then once we get the derivative, From that
you
point,
plug in 100 in the derivative, and that will predict how much it will cost to make 101st item.
about the 102nd.
Exactly. Exactly. So this particular example shows us which of the two methods is easier, to find the derivative and plug it in, or plug in the cost function 101, plug in the cost function 100, and then subtract. I have to be honest, if you want an accurate, 100% accurate result, you will always have to do this. If you're okay with a minor error because of speed and you want to get an answer quick, you want to look at the marginal cost and plug it in to see how much it will cost you. Here, you have to have the function. Of course, even for the derivative, you have to have the function. But remember, there are other ways of not having the function but finding the derivative. What am I getting at? I don't have the function, but I can find an expression for the derivative. How is that called? Wonderful. Yep. So we're going to come back to this in section 3.10. Okay, I'm ready now to start 3.9. 3.9 is big. So,
Can we actually do the implicit differential numbers?
say it again.
If we have time, we actually do the implicit differential numbers.
You don't need it because you have the function. But if you don't have the function, you use implicit differentiation.
Around the same level.
Yes, but if you have the function, then you are determining the derivative directly, not implicitly. You're using implicit because you're going like this instead of going directly. If I have the function, I go directly to the derivative. But if I don't have the function, I go implicitly to find the derivative, an expression for the derivative. Because you may still have the function in it, which I don't have. Okay. I gave you the handout 3.9. So let's look at those problems, or we can choose other problems you want from your book. They all come from your book, actually.
This is the one where like it's like you have to sample two samples times and that, like,
Yes, and you want to determine, exactly, that's a perfect example. I think I have, yeah, that's probably you read this in number 2. Yes, so what we are interested in is this. So for example, as Ian said, so starting from one point, 2 people walk in opposite directions maybe, or at a right angle. So one goes, for example, west and the other one goes north. And there is a distance between these people, right? So if they're here, the distance is 0, but one runs and the other one walks. So the question is, how fast is the distance changing between the 2 of them at some point in time? And that's related rates. Yes. So when 2 or more variables change at the same time, okay? So we are given the following equation. So let's start with that. Simple. We are given the following equation. X squared y equals 18. Here we're asked to find dy over dt if dx over dt is 10. So I want to start with an example that is just does not require a lot of thinking. Just a simple plain example. So this is 3.9, related rates. Okay, so we have x squared y equals 18. So we're asked to find dy over dt, and we are told that dx over dt is 10, and x equals 2. So the question is, find dy over dt if these are given to us. Let's look at the equation. It's an equation. It's x squared times y equals 18. Can I solve for y if I want to? Yes. Can I determine dy over dt implicitly? So simply differentiating both sides? I can. I don't have to solve for y. So when I'm asked to determine dy over dt, what do I know for sure about t? There's one thing I know I have. in my mind about t. I know that about y. I know that y is
It's a function of t.
excellent. Okay, now let's continue reading. Look at what this says. This says that dx over dt is whatever. What does this mean? Forget about the number. X is also a function of t. So there are two functions in here, x and y, and they are both depending on a variable. They are both functions of a variable called t. So then when I differentiate both sides here, what do I get? Yes, oops, my tent is falling apart.
X times y
Excellent.
dt
Plus, it's a product rule.
plus 18.
So first of all, forgive me, x is a function of t. So let's start from the beginning. 2x times, I should erase the whole thing. It's easier if I start in a different spot than writing over there. So one more time. X is a function of t. Y is a function of t. Tony?
2xy.
Careful.
dt.
Yes. dx over dt times y. That's okay. It's correct. Everything you
okay,
said
okay.
is perfect. I just want to write it one next to the other.
Got it.
So I differentiate x squared. I get 2x dx over dt times the second function, times the second function, plus, I meant to say, plus what? X squared.
Y times y.
There is no y. Yes. dy over dt equals 18 prime. I cannot just differentiate one side, which is how much? Yes. A constant prime is 0. Good. Okay, so now I'm asked to find dy over dt, so we'll solve this equation for dy over dt, moving this to the other side. So x squared times dy over dt is negative 2xy dx over dt. Perfect. So what should I do now to both sides to get dy over dt? So dy over dt, I divide both sides by x squared. So negative 2xy over x squared times dx over dt. Of course, I'll simplify one of them. So dy over dt. And now, only now, I'm using the given information in the problem. I am told that dx over dt is 10, and I'm told that x equals 2. So I write negative 2 multiplied by y. I didn't calculate it yet. Here's my equation. X squared y equals 18. I am told that x equals 2. I need to determine y. How much is y? I have 18. I have 4. 4y equals 18. So then y equals 9 divided by 2. 18 over 4, 9 divided by 2. Correct? Are you with me? So 9 divided by 2, everything divided by x, which is 2, and everything multiplied by dx over dt, which is 10. Let's look at this for a second. I'm checking the time here. Okay. Any questions? So I copied negative, I copied 2, I copied x in the denominator, which is 2. I copied y from here, I had to calculate, it was not given to us. So I have 9 over 2. And dx over dt is given to us as 10. I simplify and I get a number. So 9 over 2 times 10. So when I write it again, let me write it again. 9 minus 9 over 2 times 10 over 1. I simplify and I get negative 45. And that is the rate of change of dy with respect to time, or x or y with respect to time, or the derivative of y with respect to time. Okay, so now we can look at application. Yes, Tony?
I know this is probably a gross oversimplification multiplication, but this is just implicit differentiation, except now we have the extra, possibly have the extra step of looking at
Right.
solving another.
Right. However, this was just basically a warm-up type of problem, because in real life situations, I will have to find the function or an equation. Here it was given to us.
Got it. Okay.
Okay? So, for example, in the next problem, we don't have a function. But I'm asking you find its derivative. So you will say, I can't find the derivative before I find the function to differentiate. So I will be asking you find the derivative, right? Or how fast is the distance between those two changing at blah, blah, blah. So I'm asking you not just to find the derivative, but also evaluate it. But if you don't have a function, you will not have the derivative, and you will not have the value of the derivative. So let's read the next problem. Okay, so at noon, ship A is 150 kilometers west of B. So this is problem 2 on the handout. A is west of B. 150 kilometers between the two of them. A is 150 west of B. A is sailing east. Right? So A is going this way. And at 35 kilometers per hour. Meanwhile, B is sailing north at 25 kilometers per hour. How fast is the distance between them changing at 4 p.m.? I'm going to write it as I did, and I'm going to, you don't have to do this. I'm going to cross it out just to remind myself, only to be used at the very end of the problem. Like we did here. I did not even look at these two numbers till I obtained an expression for dy over dt. When I obtained an expression for dy over dt, then I went back and said, okay, where are my numbers? I collected them here at the very end after I found dy over dx. I'm sorry, dy over dt. Then I was ready to plug in the numbers. So I will never, ever look at something like this till I have the function, I differentiated it, and I'm ready to plug in numbers. Okay? So here's the scenario. They are 150 kilometers apart, and they start moving like this. One more time. So the distance between them is 150, and they start moving like this. Imagine there is a line between these two. And you see the line, and it's changing. This line is changing. So this is what I'm interested in. I'm interested to find the rate of change of this distance when blah, blah, blah. So what do I have to do? I have to look at a scenario, which is a generic scenario. And here's the generic scenario. I don't want to call this distance because then I have dd over dt, and I don't want to have that. So I'm going to call it w. So this is what? And what is this? And I know that the whole distance is 150. So one more time, they start sailing. What is this? What is this piece? Till a certain moment in time, not 4 hours, a certain unknown moment in time. I'll say stop. What is this distance? The distance covered by ship B. What is this distance? Distance covered by ship A. Good. So how do you want to call them? Because this is on the x-axis, let's call it x. Because this is on the y-axis, let's call it y. Obviously, this is what here? Good, a right triangle. So this is w, this is y, and how much is this? How much is this piece? At the particular moment in time, we don't know that. Well, if this is 150 and this is x, I know that piece. How much is it? Makes sense. Good. So I have all sides of this right triangle. What do I do with the right triangle? Always. There is something I can write in a right triangle always. Nope. The leg squared plus leg squared equals hypotenuse squared. I have to apply it here. Because unless you show me where is A and where is B and where is C, I can't agree. You understand? I'm not saying it's wrong. I'm saying you haven't shown me the triangle, so I can verify that you are adding the legs squared. Indeed. Very good. 150 minus 150 minus x, everything squared. Yes? Yes. Okay. So let's read the question one more time and make sure and we understand what we're trying to do here.